In this video, we'll look at magnetism. Magnetism is a phenomenon produced by motion of electric charges, which causes attraction or repulsion between objects. So, we look at the magnetic field. The magnetic field is that region around a magnet or a current carrying wire where magnetic force is felt. And what is magnetic force? Magnetic force is that attractive or repulsive force that is exerted between the poles of a magnet or electrically charged moving particles. This is to say now that magnetic field can be produced by a magnet or a current carrying wire. Magnetic field can be produced by a magnet or a current carrying wire. Current carrying wire. So a magnet has magnetic field around it. So if this is a magnet having the north and south pole, this is, let's use this for the north and this for the south. So it has magnetic field around it and is denoted by the magnetic lines of force which runs from the north pole of the magnet to the south pole. So the magnetic field lines runs from the north pole of the magnet to the south pole. You see, these magnetic field lines, this magnetic field around a bar magnet is being represented by magnetic field lines. Likewise, we say that magnetic field can be created in a current carrying wire. So a current carrying wire has magnetic field around it. So it was in 1820 that Hans Christian Ørsted found that when current flows in a wire, the magnetic field is created around it. So if this is a wire and current flows in this direction, so it is said that magnetic field flows around magnetic field is created around this wire, and the direction of this magnetic field can be verified using the right hand rule, right hand grip rule. So this magnetic field is denoted by the symbol B. The magnetic field is denoted by the symbol B and is a vector quantity. The unit of this magnetic field is Tesla or ampere per meter. It has another unit of Weber per meter square. So the equation that helps us calculate the strength of this magnetic field is given by this. So this is the strength of the magnetic field is given by this. This is mu naught I upon 2 pi r. So this is the magnetic permeability or the permeability of free space, which has this constant 4 pi times 10 to the power of minus 7 Henry per meter or Tesla meter per ampere. So this is the current and this is the distance. For instance, if we have a current carrying wire, this is a current carrying wire in which, for instance, again, the current is moving to north and an object is placed here such that this is the source of the magnetic field. So this is the source of the magnetic field. One can decide to find the strength of this magnetic field that will be experienced by this object. To find that, we utilize this formula. So this formula helps to find the magnetic field for instance, a straight wire carrying current. So this is mu naught I upon 2 pi r, where I is current, the r is the distance from the source of the magnetic field. So we now see that as the distance between the source of the magnetic field decreases, you notice that an object that is placed nearer to the source of the magnetic field experiences a very great magnetic field strength. So you see again that the current, the greater the current flow here, the greater the what? The magnetic field strength. So the B is inversely proportional to the distance and is directly proportional to the what? The current. So we say that this is the formula that will help one find or calculate the magnetic field strength for a straight wire carrying current. And this magnetic field strength or magnetic field, denoted by the symbol B, has the unit of Tesla or ampere per meter or Weber per meter square. So to find the magnetic field for a current loop, so if this is a current loop, a circular current loop, in which we define an infinitesimal element of the length, the L, as denoted here. The distance from this point, this is the center of the loop, to this point is denoted as R, and the magnetic field is a small magnetic field experience at the center is denoted as the B. So the loop can have n number of turns. So to find that, we define the B given by the Biot-Savart relation to be nu naught upon 4 pi. You have I the L sine theta upon R square. You notice that again, as we saw earlier on, that the magnetic field is proportional to the current and inversely proportional to this. So we'll be making use of this to derive the relationship that would help us calculate the magnetic field strength for a circular current loop. So if we integrate the B, taking note of this, we have that, of course, this is circumference of a circle, 2 pi r, and this is the n number of turns. So we can integrate from 0 to this limit, taking note that nu naught I upon 4 pi r square is constant. Then sine 90, which is the angle this inclined with this radius, sine 90 is 1. So if sine 90 is 1, integral of the L will give us L. Taking note of the upper limit of integration, this gives us this, because this will be 0. So if you now do cancellation, you have that B is nu naught Ni upon 2R upon 2R. Of course, to be consistent, this should be small r, this should be small r, so that we find out B is this. Magnetic field along the axis of a current loop. So this is the magnetic field at the center of a circular current loop. So going further, we defined what a magnetic moment is. This is a vector that describes the strength and orientation of a magnetic source, like a magnet or a current loop, and it essentially measures how strongly a magnetic object tends to align with external magnetic field. So to find the magnetic field along the axis of a solenoid is a coil of wire, we use this, that B equals nu naught NL, where this N is number of turns per unit length. So if this is a solenoid, of course, solenoid is a coil of wire. This is a solenoid. So of N turns, N number of turns. So this is the length of the solenoid. This N is given as the number of turns per unit length. So basically this is nu naught N. Of course, this is I, nu naught N upon Li. So this relation helps us to find the magnetic field along the axis of a solenoid. So as an exercise, you should write the expression for the magnetic field in a toroid. A toroid is just a circular what? Solenoid. A circular solenoid. So I've said before now that one can create magnetic field around magnets or current carrying wire. In our next video, we shall solve problem using this formula for magnetic field strength. Do have a wonderful day.